So the final exam is going to be non-cumulative. That's the most important thing to remember. So you are not going to be going back and being tested on anything from units 1, 2, and 3 unless it's specifically recapped again in unit 4 in some way. You know, maybe like something with plate tectonics. You need to know the basic gist of plate tectonics to understand what's going on with some of the stuff in unit 4. But other than that, this is a unit 4 exam, and it's going to be exactly the same format as the other 3 exams in this class. So it isn't really a final. You know, it's just a last exam that happens to be taking place during finals week. I was really hoping to avoid all of the confusion with finals week altogether by having us take our exam before Thanksgiving, but we just missed so many. We had to push back, I think, multiple exams, and all that confusion happened. I wanted to make sure everybody had as much time as possible to get through this Unit 4 stuff and to watch all the videos. So I went ahead and had to deal with finals week and all the confusion there. So that's what's going on there. But hopefully that gave you plenty of time to get through everything. As always, if you have any questions, you're very welcome to go ahead and just shout them out. And that's your best chance of getting your question immediately answered. Otherwise, if you'd rather use the chat box, you can do that. And I'm going to be going back and forth between a Word document and the screen. So I may not get to the question right away, but when I do, I'll come back and I'll answer it. So any questions, comments, go ahead and stick them in the chat box. I'm going to go ahead and get started. And as always, I like to use the review questions that I post as a way of recapping the material. It's in no way completely, oh, wait, I forgot to do this. Let me go ahead and do share screen so you can actually see the stuff on the other screen. Otherwise, this is going to get real confusing. As always, I'm going to use these review questions, and they do cover the big picture of everything that I'm going to be, that everything is going to be fair game for the exam. It's like the big picture concepts, but it's not everything. So there's definitely going to be things that don't make its way to this review. If you want more of a comprehensive study guide of all the individual points you need to know for the test, I would look at the individual lecture outlines. So this is lectures 20 through 25, going from relative age dating, absolute age dating, and then all of the lectures 22 through 25 are basically parts of Earth history, starting from the beginning and then working our way up to present. So the final 4 lectures are basically just a very abbreviated timeline of Earth history. So going over to the review question list, I have these all, as always, in order from the kind of material from the first lecture on down to the later lectures. So question 1 on relative age dating, that's going to be a question from lecture 20, all the principles of relative age dating. Question 2 here, describe how the age of the Earth is calculated. That's something that I covered in lecture 21. And then I also covered in lecture 21 radioactive decay and the types of radioactive decay. That question in particular, I believe that was the extra credit assignment question, and it's also really, really helpful towards sort of understanding how to get at those problems on the final. You know, because especially if you don't have a big back history in chemistry, it can be a little bit daunting, but there's a pretty easy trick to remember the different types of radioactive decay. So we'll go over that trick in question 3. And then questions 4 and 5 are basically sort of from lectures 22 through 25. I'd say for this final, you really, really want to make sure that you've watched even maybe multiple times lectures 20 and 21. That's going to be like the bulk of the final. And then maybe the first half of 22 when I cover the geologic time scale and I kind of go over these different terms that I use as far as the names of the eons and eras and periods. And then you definitely want to have watched 22 and 25, but they're through 25, but that they're going to be featured less heavily on the final. So it's definitely worth your time to spend the majority of your time on the first half of all of the lectures, so 20 through the first half of 22, and then less time on the rest of the lectures. So let's dive straight into question 1 up here. What is relative age dating? Relative age dating, I'm just going to want to change my formatting around. I don't want you to do that. Hang on. Give me just a second. That's going to annoy me. All right. So relative age dating, sorry about that, is the process of putting events in sequence, but not assigning an actual age to those events. So in relative age dating, we seek to understand Earth history by looking at the succession of events and looking at what came first, what came second, and so on. You can basically sort of tell the story without actually assigning any ages to any of those events. So take, for instance, the Rocky Mountains are newer mountains. They formed more recently than the Appalachian Mountains. That's an example of relative age dating. You know about the events that formed both of those mountain ranges, and you know that the Rocky Mountain orogenies happened more recently than the Appalachian Mountain orogenies. So that's an example of relative age dating. Whereas if I said the Rocky Mountains started forming 65 million years ago, that's an example of absolute age dating. So in question 2, when I say describe how the age of the Earth is calculated, we're going to be using absolute age dating techniques, specifically radiometric age dating, in order to understand the true age of the Earth. So relative age dating is a little bit different, but the origins of how we understand geology are in relative age dating, and it's incredibly important to be able to put these events in sequence to be able to sort of tell that story, because it's really difficult to come up with radiometric age dates, especially for events where you don't actually have the material left behind, like the formation of a canyon, or even in some cases, the formation of mountains. You can't exactly radiometrically date some of those events. So give me 1 second. I think I have somebody I need to admit into the meeting because they're coming in from an external source. And we'll come back over here. So that's part 1 of the question, what is relative age dating? Part 2, what are the principles of relative age dating and how are they used? So we're just going to go over the most important of the principles of relative age dating. I'm not going to cover all of them from the lecture. So, you know, I'm sure somebody's going to go with, but what about uniformitarianism? Or what about original horizontality or something? Don't stress it. I'm just going to cover the most important ones so that we can kind of get those concepts down. Then, you know, the rest of those are mainly all sort of rules that make the most important concepts work. So the first one I want to talk about, the most important in terms of actually doing relative age dating, is the principle of superposition. The principle of superposition states that the majority of rocks, especially sedimentary rocks, are all laid down in sequence with one on top of another. So in a body of water, when you're talking about clay or sand falling out of solution and depositing on the bottom of something like a river channel or a lake bed or the ocean floor, they're all deposited one on top of the other. So we can look at this basic rule, the principle of superposition, how those rocks are formed in the first place, and know that layers of rocks, let's see, layers of rocks found deeper are older than layers that are closer to the surface. So a stratigraphic layer that's maybe 200-300 feet below us is going to have formed a much longer period of time ago than the sediment that's right underneath your house. Now, when you're dealing with events that have overturned rocks, then you don't necessarily still have this relationship where the oldest is on the bottom and the youngest is on the top. But that's why this principle is so important, because at least you know that the rocks were originally laid down in that sequence. So no matter what happens later, you can still figure out what was formed first and what was formed second and so on. And you can still do relative age dating on those layers. I'm going to skip the principles of original horizontality and lateral continuity. Those are basically rules that make the principle of superposition work. We know that the rocks are laid down in roughly uniform thickness, and were originally laid down flat. They were originally horizontal and laterally continuous. And so that makes superposition work. The next one that's really important, so superposition was Steno's law. The next one that's really important is the principle of cross-cutting relationships. This basically says that anything that cuts through a sequence of rock, and those things that cut through sequences of rock are usually igneous intrusions or faults, are younger than the rocks they cut through. So in order to cut an onion, the onion has to be there with all of its individual layers. And it's the same thing in geology. Those layers of rocks that get either faulted, or if an igneous intrusion pushes up and migrates through pre-existing rock, those events have to be younger than the rocks that they cut through. And so that can sort of offset the principle of superposition in some cases, especially dealing with igneous intrusions. Now, intrusions are different than inclusions, because intrusions are new rock that's pushing up through pre-existing rock. Inclusions are old rock that gets embedded in a new rock. So they're very similar terms, and it's one of the more irritating things about this particular branch of geology is how similar the terms are, and I apologize for that. But this next one coming up is the principle of inclusions. So that means pieces of pre-existing rock, those are the inclusions, must be older than the rocks they are embedded in. So if you have some layer of granite and pieces of that granite get embedded into an overlying layer of sandstone, that's just saying that that granite was already there and it's older than the sandstone. And so all of these are just tools that can sort of help put events in sequence. The last one that's particularly important in terms of relative age dating, again, there are things that we're skipping, like the principle of faunal succession. That it isn't as useful to relative age dating as some of these others. The last one that we're going to cover that's particularly useful here is the principle of landscape succession. They all have very grandiose names, but they're all super logical and super intuitive. So the principle of landscape succession just means that any erosional features, similar to the principle of cross-cutting relationship with faults and igneous intrusions, any erosional features must be younger than the rocks they have eroded. Canyons are younger than the rocks that make the walls of the canyon. Take, for instance, the Grand Canyon, which is always the really obvious choice to go back when we're talking about any kind of canyon geomorphology. The Grand Canyon had all of those layers of rocks pre-existing and the river cut through the canyon, as opposed to having these rocks just sort of grow up on either side. So the much more sort of logical thing that's consistent with the laws of geology would be that the layers of rock were already there and the river cut through those layers to form the canyon. So the canyon must be younger than the layers of rocks that are exposed on either side of the canyon. Okay, so that is just some of the principles of relative age dating and the ones that are sort of most useful when you're actually using these principles to determine the relative age of something. Like I said, there are other principles, but in the interest of time, these are just going to be the main ones, these 4 that we covered. Now, I'm going to stop for a second, go back to our main screen, make sure that everybody's good so far. Please, please, please let me know at any time whether I'm in the middle of a question or not, if you have any questions, and I would be more than happy to help. So with lecture 20, while I'm waiting to see if anybody has questions, that one is, I think, generally pretty easy to understand, pretty intuitive, and for the most part, most people don't have any real problems with that. There are all of these terms that are a little confusing, maybe a little hard to grasp, the different types of unconformities, but it's much more apt to like a memorization, the way that a lot of people tend to like to try to learn something, than some of these other concepts that we do. So for the most part, lecture 20 is usually pretty good for most people and pretty easy. So this next bit of material, when we get into absolute age dating, that gets tricky for 2 reasons. It's not as directly intuitive, 1, and then 2, it can be a little tricky because we have to get back into chemistry again. And if you have a good back history in chemistry, then no problem. But if you're trying to sort of learn chemistry too, that gets a little tricky. But I'm here to give you some assistance with that and some easy tricks, especially when we get into question 3. It's why I have 2 questions from this one lecture, lecture 21. So the first question is, describe how the age of the Earth is calculated scientifically and explain how we can make this calculation based on our understanding of how the Earth formed. Now, at the beginning of lecture 21, I went through several sort of failed attempts to get at a scientific calculation of the age of the Earth, starting with like a somewhat non-scientific calculation, and that's the 6,000 year calculation that Archbishop James Ussher came up with in the 17th century. And then going into some of the others, you don't need to know any of the details of really sort of the failed attempts, like Kelvin's attempt, anything like that. Just that for whatever reason, it didn't account for one of the complexities of understanding Earth's geology, and therefore wasn't a true indication of the age of the Earth. So the answer to this, describe how the age of the Earth is calculated, deals with radiometric age dating of primitive meteorites. So the reason why we use meteorites to get at the age of the Earth is because we can work under the assumption that these meteorites are really sort of like these primordial building blocks of the planet itself, based on our understanding of how the Earth originally formed. So going back to the very, very beginning of Earth history and the beginning of the history of the solar system, really, we think that all of the planets were built through this process called accretion. And we can see the same process happening in other solar systems, where these particles collide. And by particles, we're talking about pieces of dust to maybe sand-sized particles that populated this nebula that was going to form our entire solar system. All of these things start to collide. Then they get bigger. They have more mass and more gravity, and they attract more particles. So you go from something that's maybe sand-sized to boulder-sized to mountain-sized to continent-sized, and you grow bigger and bigger and bigger pieces until eventually you've cleared a path through some swath of the solar system where the orbit of that planet typically lies, you've completely cleared it of all of this debris. But that process takes hundreds of millions of years. So think about how many loops around the sun that is. That's potentially 500 million routes around the sun to completely clear the majority of that orbit of all of these existing pieces of particulate. So we think that's how Mercury and Venus and Earth, Mars, Jupiter, Saturn, all of the planets formed. So let me type out some of this here. I'm doing a lot of talking, not a lot of typing here. So radiometric age dating of primitive meteorites, we use primitive or unaltered meteorites because we can assume these have been, these are, let's say we can assume these are representative of unchanged building blocks that created our planet 4.54 billion. Well, let's just say for now, billions of years ago. So we take these meteorites, and a meteorite is basically just some bit of space garbage, some rock and metal that happened to have landed on Earth fairly recently. And by fairly recently in geology, we're thinking sometime in the last 50 million years or so. And we can take these meteorites and we can figure out the proportion of radioactive isotopes of particular elements to their decayed counterparts. And we can use that as sort of a clock that started at the time when that primitive meteorite formed. That would have been around about the same time that the Earth was forming. It started at that point and has been decaying ever since. And you can use the amount of decay that has taken place in order to come up with an age of not just that meteorite, but an age of the Earth and the age of the solar system. So we have these unaltered building blocks, and we can use radiometric age dating using uranium with a mass of 235 to its decayed counterpart, lead 207. A proportion of radioactive to decayed isotope to determine how much time has passed since that meteorite formed, and therefore the age of the Earth. So the first meteorite that we ever used to do this, to use uranium-235, lead-207 dating, was called the Canyon, let's say, according to the Canyon Diablo meteorite. The age of, according to uranium lead proportions in the Canyon Diablo meteorite, the age of the Earth is 4.54 billion years old. And it's important to remember that that's 4,540 million years old. So it's really hard to think about things in terms of being billions of years old, because we don't have the kind of perspective in an average human lifespan of something like 75 years to really appreciate how long 4.54 billion years is. And that's not even the entire age of the universe. We think the universe is 13.87 billion years old. So the Earth is relatively newly formed compared to the rest of the universe. I'm thinking in terms of the universe because I just did a 102 lecture, and that was the final question, sort of birth and death of the universe. So that should wrap up that question pretty well, and it kind of covers material from the first half of lecture 21. Does anybody have any questions on that, on radiometric age dating, any of those processes? So like I said, lecture 21 is a really loaded lecture. It's probably the most difficult conceptually of all of these lectures of the last unit. So definitely deserves watching, maybe even re-watching to just kind of make sure you get everything down. The second half of that lecture goes through the types of radioactive decay that can occur and some examples of those types of decay. So this is also the extra credit assignment question. It's a little dry for an extra credit assignment question, honestly. You know, like if I was just looking for like more fun, juicier answers, I probably would have picked the second one instead. But I thought this third one would be more useful because it's more directly related to some potential exam questions. So the question is, what are the three forms of radioactive decay, and what is the effect of that decay on atomic number and mass of an atom? Give examples. So you really, let's see, the inherent tendency is always to kind of try to just memorize your way through everything. And when you get confused on an exam, that's the first thing that falls flat, is if you've got everything memorized and then you have something that kind of shakes you a little bit, then that whole house of cards in your head is just going to come tumbling down. Instead, it's better to truly learn these different types of decay and not try to memorize individual examples. So the three types of decay are called alpha decay, beta decay, and electron capture. Now, there's two different, technically, there's multiple types of beta decay in which slightly different things happen. There's kind of a positive and negative beta decay that we'd get into if this was a chemistry class, but I'm not going into that level of detail. In alpha decay, you lose an alpha particle, or the equivalent of a helium nucleus, which is 2 protons and 2 neutrons. Of course, both of these things, protons and neutrons, exist in the core or the nucleus of the atom, and these are the more massive constituents of the atom. The electrons essentially are just all charge and no mass, and they don't exist in the nucleus. So to lose an alpha particle, you lose 2 protons and 2 neutrons. Two things are definitely going to happen. The name of the element is inherently going to change because the number of protons effectively defines the individual element. The other thing that's going to happen is that the mass is going to change. So the second half of the question up here, what is the effect of that decay on the atomic number and mass of an atom? The atomic number, every time there's an alpha decay, decreases by 2. Atomic mass decreases by more than 2, because both the protons and the neutrons are going to compose the mass of the atom. So the atomic mass actually decreases by 4 of these units that we call atomic mass units. It's really not particularly useful in anything outside of chemistry or chemistry-related disciplines like geology. So the easy way, let's see, star here, easy trick to get through questions on the exam is anytime the mass changes, it has to be alpha decay. The way these are going to be presented on the exam are basically going to be where you have an example of some type of decay that's occurred, and then you have to pick what type of decay has actually occurred. Now I'm distracted for just a second because I'm actually pulling up on my phone the exam itself to give you at least one, maybe two examples of these kind of questions straight off the test. So bear with me for just a second. I'm in the wrong class. I'm in 102. Okay, 101 exams. Okay, so here's one. All right. So the question, and don't worry about trying to copy this down right this second. If you're, going, oh no, she's giving an exam question, I'm going to actually type it out later. But the example that I'm going to give you involves something called rubidium decaying into strontium, and the mass has not changed. So when you do kind of try to come up with your answer to this question off the test, you can scratch out alpha decay because you know the mass has to change if it was alpha decay. I'm going to go over the other two options, and then I'm going to actually write out the text of the question, and we're going to come up with an answer. So with beta decay, it becomes a little bit more difficult, especially to distinguish beta decay from electron capture, but we're going to do that next. So beta decay is what's going to happen when you have effectively an electron capture. An electron being ejected from the nucleus of the atom. So what's happening here is you lose a negative charge from the nucleus of the atom as a neutron changes to a proton. So let me scroll down here so everybody can see the entire thing here. So beta decay, you effectively lose a negative charge, and the reverse is going to happen when you're dealing with electron capture. So if you lose a negative charge from the nucleus of the atom, what's actually going to happen is the entire nucleus is going to become more positively charged as a result. You're going to take a neutron that was neutrally charged and change it to a proton. Now, the things that are going to compose the mass of an atom are going to be the neutrons plus the protons. And because you're changing one into the other, you haven't actually changed the mass. You can have 99 neutrons and one proton, or you can have 99 protons and one neutron, and the mass would still be 100. So what's going to happen here, the actual result to the nucleus of the atom is that the atomic mass does not change because you still have the same total amount of neutrons and protons together. But because you've taken the neutron and changed it into a proton, you have one more proton. So the atomic number will increase by 1. So here's my easy trick. If you move along the periodic table, if you move forward on the periodic table, so towards the right or from one row down to the next row, if your atomic number is what's increasing, then it has to be beta decay. If you move forward on the periodic table, it has to be beta decay. So give me just a second here. I'm going to show you guys, let's see. Give me just a second here, periodic table. I thought I had one on the website here, but basically any periodic table, you guys, is going to have 2 numbers on it. And I'm trying to kind of make this as easy for you as possible. So I want to make it really clear that you are to completely ignore anything going on at the bottom of each one of these blocks on the periodic table. Ignore it completely. In the text of any question I give you on the exam, I have to give you the mass. So the number that I give you has to be the mass. So the number on top, this 24 up here for chromium, or the number 6 for carbon, that is the atomic number. And that's the only number that you have to look at the periodic table to figure out what type of decay is occurring. So if you were dealing with a case where you were dealing with radiocarbon decays into nitrogen because you move from atomic number 6 to atomic number 7. You have to be dealing with beta decay. If you had some weird type of decay that isn't actually real, where let's say fluorine decays back into oxygen, but the mass changes the mass does not change, but you have fluorine that's decayed into oxygen, then that can't be beta decay, because beta decay has to be moving forward, 5 to 6, 8 to 9, 27 to 28, and so on. So always moving in the direction, the increasing direction on the periodic table. If you're having anything that's moving opposite of that, like potassium decaying into argons, 19 to 18, any case where you're decreasing in the number, your atomic number, that's when you're going to be dealing with our last type of decay. So the last one is electron capture. I already wrote it down over here. Electron capture. In this case, like the term capture would imply, you gain a negative charge into the nucleus of the atom. And a proton changes to a neutron. So it's the exact opposite of beta decay. So same thing applies here with beta decay, that your atomic mass isn't changing because your total number of protons and neutrons remains the same. So atomic mass does not change, but the atomic number will, in this case, decrease by 1. With all of the examples that I'm going to give you on the test, all of the examples that I've given you in the books, you're dealing with a case where the type of element that you're dealing with has to change. You have to be moving from carbon to nitrogen or uranium to thorium. Something like that has to be happening, because in each and every one of these cases, your total number of protons is changing, and it's the number of protons that defines the element. So going back to the periodic table real quick, if you were dealing with something where you had, let's say potassium to argon, again, that's an actual real example, or to give you sort of like a fake example off the top of my head, let's say this beryllium decayed back into lithium, that's going to be electron capture, because you're moving backwards on the periodic table. So you're moving from right to left on the periodic table, and instead of the advanced direction, which is left to right. So the question that I'm going to give you off the exam, I was alluding to earlier. Let's see. Goes as follows. What type of radioactive decay, this is how all of these kind of questions are going to be worded, what type of radioactive decay occurs when rubidium I'm going to write it as this, rubidium-65. You'll often see it as a superscript to the left of the name of the element too. So either way, you're just dealing with mass. So rubidium-65, rubidium with a mass of 65, decays into strontium-65. So I'm going to go back to the meet and see who's still alive and with me as we Oh, cool. I've already got a question on this. So somebody's alive with me. All right. So your answers are, oh, sorry, to answer these questions so far. Let's see. Jacqueline, is there going to be a periodic table in the test? Absolutely. I have to give you a periodic table. It's basically going to be, I will write it into the directions on the test exactly how you get to the periodic table, but I'll make it really easy to get to. It'll be super obvious how to find it, and it'll be in the lockdown browser. You don't need to print it off in advance or do anything fancy. Statement down here, let's see, is gamma decay related or connected to electron capture or something? Gamma decay is actually not a type of decay. I think I worded it a little differently on the test. I didn't give this option, but I threw gamma decay in as like a fake option, you know. So I think for the quizzes, maybe I think I had the options of alpha, beta, electron capture, or gamma decay, mainly because I think I was in multiple choice land and I needed a fourth option, you know, so I went ahead and threw that out there because it sounds like another option, you know, but that wouldn't have been correct. It would have been one of the other options. Another note about the quizzes, if you're going back and you want to look and figure out what you did wrong on any of the quizzes, you can always go click on your quiz attempt under grades. You go under your grades, you click on, let's say like quiz 22, and you'll pull up the quiz and it'll show you all the correct answers now. If you looked at it right after you took the quiz or while it was still open, I don't have the correct answers shown up until later on once it closes. So you can always go back and review those. And I definitely would advise everybody to do that, whether or not you got them right, because they're similar questions to the kind that I would ask on a test. Going back to the question here, what type of radioactive decay occurs when rubidium-65 decays into strontium-65? So your options, and here's the periodic table, here's rubidium, here's strontium. So your options are alpha decay, beta decay, electron capture, or D, answers A and B. So let's go through and rule them out. Or actually first, does anybody want to throw out an option? Is it alpha?
Would it be beta?
Let's take a look. I can't remember off the top of my head. It is indeed beta, because you've got rubidium decaying into strontium, so you're actually increasing your atomic number. If rubidium was decaying into something really weird and unusual, which doesn't actually happen in nature, like krypton, then it would be the opposite. It would be electron capture. So as you're going through your answers, you know you can eliminate alpha decay as a possibility because the mass didn't change. And you know that between electron capture and beta decay, it has to be beta decay because you're progressing forward on the periodic table. So throwing out another option here that I always like because it's one of the steps involved in the calculation of the age of the Earth is the decay of uranium. When uranium decays, when uranium-235 decays, it decays into thorium. So because the atomic number has decreased by 2, and because the mass has obviously changed, and that would be indicated in the text of the question, of course, that has to be alpha decay. And you more often find alpha decay occurring in these really super heavy elements at the bottom of the periodic table, because everything past lead, bismuth, all the way down to all of these crazy elements that barely exist in the real world at all, those are all going to be radioactive, and they're all decaying backwards. They're all losing a substantial amount of mass to eventually get down to lead. Okay, so any questions on radioactive decay, on the extra credit assignment? Basically, as long as you gave me the gist, those 3 types, how to tell them apart, you're in good shape, and you're in better shape for the exam too. Okay. So I think we're probably.
That question is beta decay.
I'm sorry, what was that?
The answer to that question is beta decay.
Yes, yes. I will write it down. Yes. So what type of decay has occurred? It is beta decay. All right, so from here on out, the last two questions are basically going into that sort of chronology of Earth history that I start halfway through 22 and carry on through 25. But you've probably seen in the quiz questions that I have a lot of questions on the quiz, and I'm going to have a fair number of questions on the final that just deal with the names of eons and eras. And that's explained really, really thoroughly in the beginning of lecture 22. So I will ultimately come back and I'm going to answer these two questions, 4 and 5. But I thought it might be even more useful to go back to this main page and look at this picture real quick. I had a picture like this for, I know the very bottom of this is hidden and I'm sorry, but there's a 1 right at the very bottom of here. But I had a picture similar to this for all of the units that was just sort of like.
You can click the hide button, I think.
Okay. Cool, thank you. Okay, I was a little nervous about clicking on that because I didn't know if it would hide it from you guys. Can everybody still see the geologic time scale?
Yes, I can.
Awesome, okay, cool. I'm gonna assume that's representative of the whole. Thank you. Okay, so you had a picture like this, like a big picture picture for all of the units, for units 1 through 3 as well. But this one is particularly important for unit 4. And in the past, I used this sort of altered version where I had these 10 places on the time scale to do kind of a project with my 101 classes and to kind of like make it easier to go into the final. So I didn't exactly do that route with you guys this semester, but this is still pretty useful. And this at least kind of points out the biggest events. I go into a lot of detail in the second half of lecture 22 all the way through to 25. And this helps you kind of weed through like the big events kind of timeline for Earth history. So as long as you've got these events down, you're in pretty good shape. And this is a good place to kind of go through and do a quick recap of eons and eras. Now, okay, you're responsible for the eons, and there are 4 eons in Earth history. Those are the Hadean, basically I think of like hell world, right? The first 500 million years of Earth history. The Archean, that's going to be the point from 4 to 2.5 billion years ago. So it represents about 1.5 billion years. And that's when Earth still sort of looked somewhat like it does today, but it was very different because it didn't have oxygen in the atmosphere or dissolved oxygen in the oceans. So you only had very primitive life during this big chunk of time. You had red skies, green ocean, so it's kind of weird world, you know, almost water world for a long period of time. Starting at 2.5 billion years ago all the way up to about 500 million years ago is this eon called the Proterozoic. And I think of this one as sort of Earth Mach 1 in terms of life, because you start to see a real emergence of bacterial life, and towards the end of the Proterozoic, you start to even see macroscopic life develop and then really come into its own in the Phanerozoic. So the Proterozoic and the Archean, and even maybe potentially parts of the Hadean, you basically just have the world being dominated by microscopic life, mainly bacterium and other microscopic life. Then in the last 500 million years, the Phanerozoic, that's when you start to get into the evolution of macroscopic life, so big things, mainly because oxygen was enabled in the atmosphere, and that oxygen enabled large-scale life to develop. So you have to know the eons, and there'll be plenty of questions on the exam about the eons. Which eon are we in now? We're in the Phanerozoic. And which eon did oxygen become abundant in the atmosphere? That was the Proterozoic. which is the first eon of Earth history. It's the Hadean. The Proterozoic actually represents the longest chunk of time, because that's almost 2 billion years of Earth history. And even though it's kind of stretched out in an exaggerated way here, the shortest eon of Earth history is actually the Phanerozoic, or maybe arguably the Hadean. But the Phanerozoic represents the same amount of time as the Hadean. It's only roughly about 500 million years. But it's the 500 million years that is the recent 500 million years, and it's the chunk of time that we know the most about, and it's the chunk of time where large-scale life developed. So it's super important. So you need to know eons: Hadean, Archean, Proterozoic, Phanerozoic, and you also need to know the names of eras. You can get away without knowing the periods. I'll occasionally talk about the dinosaur extinction, for example, as the KT extinction, Cretaceous Tertiary, because those are the abbreviations we use in geology. But I'll also talk about it as the end Mesozoic extinction to try to make it as user-friendly as possible. So you need to know the eras as well. And the eras are how you break down eons into further increments of time. Paleo means old, Meso means middle, Ceno means new. So it literally means old, middle, new life. Phanerozoic means visible life. Zoic always means life. Proterozoic means early life. So when you break those words down into what they mean, it makes a huge difference trying to remember with the order of operations of all of these chunks of time. So the way that I'm going to tackle these last 2 questions on the review questions is basically to do the first 5 events that are sort of marked off on this time scale. It's definitely not everything, but it's what I would consider to be the major events. So then take all of those little details from those lectures and kind of put it into that framework of the big events. And if nothing else, remember the big events. And then the last question, question 5, are what are the big events of the Phanerozoic? So then I'll do parts 6 through 10 on this time scale. So I'm going to write that out right here for these last 2 using the numbers on the time scale in Moodle. What major changes did the Earth go through in the Precambrian eons? Precambrian is a word that we use to denote everything that is not the Phanerozoic, not the current eon of geologic time. So going back to the time scale again, here's the Cambrian. So anything that came before it is Precambrian. So what major changes did the Earth go through in the Precambrian eons, the Hadean, Archean, and Proterozoic? Ah. So 1, 2, 3, 4, 5. Pull those over to make it a little bit easier to read and stuff. First event on that time scale, the very bottom of the time scale, has to then be the formation of the Earth itself. Or the accretion of meteorites. So this isn't just the formation of the Earth, it's the formation of the entire solar system, but because this is a geology class, we're not dealing with astronomy, we specifically kind of cover the Earth's formation. So all of these pieces of particulate, all of this material accreting together to form bigger, 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 and bigger, bigger pieces, that all generates a tremendous amount of heat. So the first 500 million years is really the process of the Earth sort of almost continuing to form after this earlier formational process, that cool off in the formational process, and a literal cool off of the surface of the Earth to the point where you can really start to form an atmosphere and oceans. Because the Earth's surface has to actually solidify. You need a crust to form on the surface of the Earth that wasn't originally there. Because every single accretionary event, every single collision between particles melted some part of that surface, and then you have to cool that back down again. So that's why that first 500 million years is incredibly hot. So going back to the time scale again, so that was event 1 down here. Event 2, 500 million years later, happens after the surface actually has a chance to cool. And that's when you start to form the atmosphere, of course, and formation of the oceans. The oceans were originally thought to not be salty. They were probably freshwater. They became salty over time through dissolved load sediment off the continents and through water cycling through mid-ocean ridges and mid-ocean vents. But you have the formation of the oceans happening sort of almost in sequence with this cool down of the crust, outgassing to create this atmosphere, and cooling of the atmosphere to the point where you could actually get the water vapor to condense in the atmosphere and fall as rain and form the oceans. So we go from hell world to water world. And then event 3 up here, somewhere midway through the Archean, is a little hazy. We don't know exactly when that happens. It's arguably older and older and older all the time, but it has to be the first continents. You have to continue to cool down the surface of the Earth to actually have that crust fracture into individual tectonic plates, and then those tectonic plates in motion is what is going to allow for the continental landmass to form in conjunction with Bowen's reaction series and the evolution of magma. So we have continents, that means we have shallow marine environments, and then we get closer and closer to this step where life is going to change the Earth's atmosphere. It's step 4 up here, called the Great Oxygenation Event. Life creates oxygen through photosynthesis. Cyanobacteria building these algal mats and these structures called stromatolites would start to pump oxygen into the oceans and into the atmosphere, dissolved oxygens into the ocean, and then oxygen, molecular oxygen into the atmosphere, which is going to completely revolutionize the planet and make it possible for large-scale life to later evolve. And large-scale life would have probably evolved much sooner had it not been for the next event, which we call Snowball Earth. Supercontinent Rodinia plunges the Earth into a total glaciation. So the reason we call it a snowball Earth at this point is because it's thought that either nearly or the entire surface of the Earth was covered with ice for some period of time, potentially up to 100 million years. So that was a huge setback in the evolution of life. It would certainly be a huge setback in my life, potentially, you know, if the entire Earth was covered in ice. It's the same for any macroscopic life form. So that's events 1 through 5 off the time scale, all of the biggest major events from the Precambrian. And this is basically the second half of lecture 22 all the way through the entirety of lecture 23 is all Precambrian geology. So these last 5, also off the time scale, are just going to be in the last 544 million years, or roughly 500 million years, and those are going to be specific to the Phanerozoic. But I want to make sure I don't have any questions, so I'm going to come back over here real quick and make sure I don't have questions. Cool, I have a yep, but I don't remember what the yep was in reference to because it was 13 minutes ago. But I think we're all good. Does anybody have any questions on question 4 or the time scale so far? Okay, if anybody's checking their watch and going like, what's happening? Okay, thanks, Ben, appreciate that. If anybody's looking at their watch and going, it's 4 o'clock, how long is she gonna keep talking? I just have the last question and then we'll let you guys go and hopefully keep studying for this exam. So, oh, back to the time scale real quick. Perspective, that's always nice. 6 was basically a line that was drawn as close to this pre-Cambrian, Cambrian boundary as I could possibly make it. So let's say it's at 544 million years ago. So this is going to be the event that defines the beginning of the Phanerozoic in geology. 7, which is going to be generally sort of the Carboniferous. So it's going to be the late Mississippian and then Pennsylvanian era, or essentially 7 is going to explain why we call this chunk of time the Carboniferous. 8 is going to be this boundary between the Paleozoic and Mesozoic. And if you're defining a boundary between eras of time named for life, if you're defining a boundary between old life and middle life, it's probably going to be a boundary where everything dies and life has to begin again almost from the ashes. So keep that in mind here, and 9 up here. We're going to be talking about events where everything dies. And then 10 is located about as close to present as I could possibly make it. So it's not going to be right now, it's going to be 10,000 years ago. So 6, 7, 8, and 9, and 10. Event 6, the event that defines the beginning of the Phanerozoic, has to be what we call the Cambrian explosion. Because just like any other discipline, we like grandiose terms. The Cambrian explosion is a life diversification event. Effectively, when specifically hard-shelled, very easy to fossilize life became really abundant, really complex, and had many different species evolved in a really fairly short period of time. And so it's just like really anything else. It's just like maybe your life, where things are going to flourish when the time is right and when conditions are really perfect. So, you know, right now in a hurricane-laden semester with a raging pandemic on, you know, like things are not ideal right now, you know, potentially. This would not be like the Cambrian explosion. 2020 would be more like snowball Earth, you know, comparing it to kind of conditions that are really ideal for your life personally. The Cambrian explosion would be some point where conditions are perfect, almost utopian for life to evolve and flourish. Now, in actuality, going back to this time scale here, life had a little bit of a head start, even maybe 50, even maybe like 100 million years into the Proterozoic, where you start to evolve macroscopic life. It's just not macroscopic life that fossilized real well. And there is a definite bias in our understanding of Earth history and our understanding of the history of life on Earth towards things that fossilize really well. And so that's how we define the beginning of the Phanerozoic, is almost a little bit of a bias. You know, if we were defining it in actual terms, one, we'd need a time scale to know exactly what was going on. I mean, a time machine to go back in time to know exactly what's going on. And we would probably define that boundary a couple 100 million years back. So we have life diversifying really rapidly, biological arms race on to really sort of dominate the terrain, but life is still restricted to the oceans at this point. Later on in the Carboniferous, life takes to the continents, especially first plants, which eventually form coal. The majority of the coal that we use on Earth comes from one particular time period called the Carboniferous. And we call it the Carboniferous because this is when plants really started to kind of take over the continents, and they they have to be the producer at first. They have to be there before animals can really come in and conquer the terrain. So you had this tremendous number of plants and tremendous number of particularly things like ferns, earlier gymnosperms, all of these plants that wouldn't have, like flowers. We don't have grasses until much later, but they were there in droves. And when those plants died and later accumulated, they would eventually form the coal that we're still using today. So I thought it deserved its own spot, especially when you take this as sort of like the very first step of life taking to the continents and conquering the continents. Because up until then, life was strictly marine and the continents were barren. So our next events here that definitely have to be stated are 8 and 9 here, the event that separates the Paleozoic from the Mesozoic and the event that separates the Mesozoic from the Cenozoic, which are mass extinctions. This first one, the end Permian, or the end Paleozoic, if you want to stick to the names of eras, is the largest mass extinction. 95% of marine species, something like 70% of terrestrial species went extinct because temperatures warmed too rapidly for life to be able to keep up with that rapid warming. And it happened most likely because of this tremendous amount of carbon dioxide that was released into the atmosphere through these really violent volcanic eruptions in the Siberian traps. So this largest mass extinction brought to you by Siberian trap eruptions. So there's certainly more to it than that, and there's this sort of double whammy thing that happens when you combine those Siberian trap eruptions, the carbon dioxide released from those, and then the later release of methane hydrates, because you were warming the temperatures from this first event that probably drove that extinction. And it's not as well known as the later extinctions, but it is certainly, in terms of the number of species that went extinct at this time, the largest mass extinction in Earth history. So after this event, we really see life on land dominate, and we see this recovery of life on the ocean, in the oceans, that has a preference towards animals that can really sort of move around, as opposed to things like corals and brachiopods and things that are stuck in one place. So the Mesozoic, this entire time period between 251 million years ago and 65 million years ago, was let's see, most infamously dominated by the dinosaurs. So the dinosaurs started to evolve all the way back in the early Triassic and really kind of came into their own, not in the Jurassic like you would think with Jurassic Park, but actually in the Cretaceous. The Cretaceous is when most of the better known dinosaur species evolved and lived. And then they all immediately went extinct with the exception of birds, right, at 65 million years ago. And that's why we define the Mesozoic-Cenozoic boundary right at that line, because the dinosaurs went extinct with many other species due to this second largest extinction. Massive asteroid impact. So we had a massive asteroid impact or large meteorite. Those terms are almost interchangeable at some point. So something the size of Mount Everest hit the very southern point of the Gulf of Mexico in a place called the Chicxulub impact. We call that impact crater that's largely submerged in the Gulf of Mexico, the Chicxulub impact crater. We're still studying it today. It's actually what my husband does most of his work on, is understanding the Chicxulub impact crater. So that was 65 million years ago. And then the last event, number 10, is only 10,000 years ago. which is, you know, the width of a microbe on that scale. 10,000 years ago, human civilizations. So if anything, kind of going back and looking at this time scale and knowing that human civilizations didn't begin until 10,000 years ago, which is so close to the top of the scale that it's indistinguishable from this top line, and the human species didn't originate or even begin to form until, you know, maybe 7 million years ago, and that's pretty indistinguishable from that top line as well. You really do a disservice to most of Earth history if you try to come up with an age of the Earth that's dependent on humans actually being present and doing something like counting back genealogies to discover the age of the Earth, because humans were not a part of the majority of Earth history. So that pretty much sums it up for me here. These are certainly not all of the events. You know, it's most of 3 lectures is, you know, what's covered in questions 4 and 5 here. But I think it's definitely the big ones. And then once you get these down, or if you've already gotten these down, I have to remember the test is tomorrow, then everything else really sort of falls into place and gives you a little bit of a framework to put those more minor events into. So coming back over here, did anybody have any other questions? Anything they want to cover from really anything Unit 4 is on the table?
I was wondering if you could reiterate when the exam is going to be, because on Moodle it says 12 to 3, and I know you sent out an email that it was going to be Tuesday 2:45 to 4:45, so I wanted to make sure I had the right times.
I totally understand. Let me do one thing so I don't confuse anybody later on. What I'll just tell everybody right now is check your email. This is 2 different sections doing their review right now. So y'all are going to have different answers. So let me stop the recording real quick so I don't confuse anybody that does this later.